Hi everyone, welcome to discussion 3 walkthrough video. Hope you had a good week so far, and we'll just dig right in. This week's discussion is on scope, static types, and linked lists. And so it's kind of a lot to cover, but we're gonna get through it. And some announcements for this week. Your weekly survey was due Monday. Lab 2 is due Tuesday. The Project 1 checkpoint is due this Friday. Lab 3 is also due this Friday. I don't know why it came up as a little fraction, but 2-5. And then carefully read the office hours guidelines if you're attending office hours, because office hours tickets that don't follow our template will be removed, not bluffing. So make sure if you're going to office hours and waiting in the queue that your ticket is correctly formed, or you will be very disappointed when we delete it. And you can read the announcements post on Ed as always for all the details. So that is it for announcements. Now we're going to start with some content review. First, let's talk about primitive types versus reference types. Primitive types are represented by a certain number of bytes stored at the location of the variable in memory. And so this is pretty much exclusively just for number types and characters and booleans. And so the way I think about it is, if let's say I make a variable like int x equals 5, in the computer or under the hood sort of, we have a variable x, right? And it's associated with some like memory box. You don't have to worry about the details, but basically directly in that memory box, we store the number 5. On the other hand, we have reference types, which are represented by a memory address stored at the location of the variable, which points to where the full object is. And so this memory address is often referred to as a pointer. And the idea here is that, let's say we have an object of any type, whether that's in a string, array, linked list, dog, etc., whatever it is, we have no clue how big that object might really be, right? It could be huge. And so it would be kind of clunky maybe if, let's say, we had like our dog D equals new dog, whatever, some big dog object. And now in memory, we have this huge object taking up space along with all of our variables. We don't know how much space it's going to take up. There's internal reasons for the computer why this is just not really as optimal. And you'll learn about that maybe more in 61C, I think. But what you need to know is that instead what we're going to do, instead of putting the whole dog where we have this variable, D, we're just going to keep a memory address. So let's say it's like memory address OX 1000, whatever the memory address would be. And then somewhere far away at that actual memory address, we'll keep the full dog. And so the details of why we do this, you don't need to understand, but just know that the primitive types you store directly at that variable, but for reference types, you store a pointer, or in other words, a reference to where the full object is. And so if you use the double equal signs comparison, it's going to compare the information at the location of the variable. So it will only work for primitive types unless you're trying to compare the memory address of two objects. So you want to use equals in that case. And so the reason I say this is, let's say we have like dog D equals new dog Fido with a string and age 10. And let's say we have dog D2 equals new dog Scruffy, age 9, or sorry, we want the same dog. So you make Fido 10 again, right? And so let's say in our like dog object, we want these two dogs to be seen as the same, right? They're the same dog, they have the same name, the same age. But if we compared them with equals, they would be different because dog D is some other object than dog D2. They're pointing to separate objects in memory, even though those objects are identical. And so because of this, if you compare them with equals, they will have different values right here. The memory that they're holding or the reference they're holding are different. On the other hand, if you did int x equals 10 or 100, because I accidentally started writing another 0, and y equals 100, at those actual memory boxes, they would store the same value, and so equals equals would work in this case. But for objects, you're usually going to want to use dot equals, because that will invoke a method that actually compares the objects themselves and not just the address. And so equals is something that is implemented by classes. So that is primitive types versus reference types. And so the next key idea to think about here is pass by value. And so pass by value means that when you call a function and give it some arguments, the function that you are calling will get a copy of those arguments you give it, and it'll be tied to its own local variables. And it is a shallow copy, meaning that if a pointer to an object is passed, only the pointer is copied and the memory or the object in memory is not. And so I think this is best explained through an example. So we will walk through this. So you start by saying int x equals 5. And so think about it, are ints primitives or reference types? Ints are primitives, and so x will have 5 stored like directly in that memory right there, right? The memory box associated with x will contain 5 directly. What about R? It's an int array. So again, are arrays primitives or reference types? Arrays are reference types, which means R is not going to directly hold this array 1, 2, 3, 5. Rather, it will hold a memory address. So let's say it has memory address 1, 2, 3, 4, and then somewhere far away in memory at that actual address will be the array. And just a quick side note, when we say OX and then some number, this is denoting that we're using like the hex system rather than decimal. And that's just convention for memory addresses, is to represent them in hex. You don't need to know much about it, but just so you know, so you don't feel confused. So we have our memory address, and so array is storing that memory address, or in other words, it's a reference to where the full array is. It's a pointer to where the full array is. And so these are all different terminologies you will hear. And then we're going to call do something with these two values. And so the key idea with pass by value is when we call do something, the do something frame will get copies of these arguments that are passed in. And so within do something, we are passed these arguments y and a. And so y is a copy of whatever x is, which means y becomes 5. And a is a copy of what r was, because that's what was passed in. And so a is the same exact memory address, which means that though a is just a copy of r, they are both pointing to the exact same thing. A is not pointing to a copy of the array separately, they are pointing to the same array in memory. And so we'll see the effects of this by walking through these two lines of code. First, we set y to be 16. And so the key idea here is that this is going to change y, but it will not change what we passed in, which was x, right? Even though we passed x in here, x will not be affected by changing the local variable y, because within the frame, the function frame, y is its own local variable having nothing to do with x. We started y by getting a copy of x, but at this point in time, they are not tied. But what happens when we execute this line? Now we say a at index 2 will be equal to 4. So here is a, and we go over to the array that it points to, and we say index 0, 1, 2 is equal to 4. And so now the array looks like this. But when we exit this method, we will see x is still 5, it's unchanged, but r, or the array, is 1, 2, 4, 5. And this is because, again, we didn't make a deep copy. So when we changed it in the function do something, it changed it for everyone who points to that array. Changing the array changes it for everyone who points to the array. That's the key idea here. And so pass by value, again, is just emphasizing that we get copies of our arguments, but they are not deep copies. And so that can result in this interesting behavior. Next, we're going to talk about static versus instance. And so static variables and functions belong to the whole class. And so an example would be if, let's say, you have a 61B student class, every student shares the same professor. And if you were to change the professor, it would change for everyone. So if Hug was like, oh my gosh, I'm so sick, I can't come in today, and then we had Hillfinger come in, everyone gets the same, like, different professor change. And it doesn't really make sense for every 61B student to have their own individual professor, right? That's just not how it works. That student to faculty ratio would be crazy. And then on the other hand, as opposed to static variables, we also have instance variables and functions, and those do belong to each individual instance. And so going back to that, again, metaphor, each 61B student has their own ID number, and changing one student's ID number doesn't change anything for any other student. And the final concept to go over today is linked lists. And so linked lists are modular lists. And when we say modular, we just mean something that can be broken down into smaller parts. And they are made up of nodes, and each node contains a value and a pointer to the next node. And to access values in a linked list, you must use dot notation. And so just to draw it out, a linked list is usually going to be represented like this. And so let's say it has like 1, 5, and so each node in the linked list points to the next node. And so if you had like int list L is this whole object, if you wanted to get like the second element, you would do L dot get and then whatever you want. And so that is what linked lists look like. And to instantiate a linked list, just like any other class, you're going to declare what type, you're going to give it a name. Here it's kind of redundant because we named our variable the same thing as a class, and then you instantiate it by using the new keyword to make a new int list. And they can be extended or shortened by changing the pointers of the nodes, unlike arrays. And so unlike an array where it's fixed length, if you want to increase the size of a linked list in Java, let's say we have linked list L, and it looks like something like this. So our first node is 1, our second node, or 0th node is 0, first node is 1, second node is 2, and that's how long the list is. And so 2's next field is null because there is no next node. If we wanted to add 3 to the end of this, it would be as simple as making a new node, then assigning 2's next to point to this new node, and then making sure our new node also has null as its next because there's nothing after that. And so it's a very easy way to extend or also shorten linked lists. And so if we wanted to now, let's say, eliminate the node 2, all we would have to do is set 1 to point to this node, and then that's it. And so 2 is out of the picture and the garbage man will come get it. And unlike an array though, you can't index directly into a linked list. So when an array, if you want the third element, it's very instant. You just go, oh, like get the third element, and there's a mechanism for getting that quickly. With a linked list, if we wanted to get the third element, we'd have to start at the front and traverse all the way until we find that element. And so that is one downside of linked lists, but they definitely have their advantages. And now we're going to move on to the worksheet. So we're going to start with static electricity. This problem really focuses on static as well as pass by value. And so these are 2 core ideas that I want you to think about as you're doing this problem. Remember our rules, which is that static things are shared by the whole class. And so changing them for one instance will change it for everyone. And remember the rule that when you're passing by value, the function that you're calling will get a copy of whatever argument you're passing in. And so this problem, the first thing to do is write what would be printed after the main method is executed. And so I want you to go through and do this problem on your own, pause the video, and then we'll come back and go through it together. Okay, I'm assuming you've paused. I missed you a lot. I hope that you had a great time doing this, and we're going to run through this. So before I even go look at the Pokemon class, okay, hi. I hope you had a great time. I missed you, and we're going to run through this problem together now. So the first things first, I'm just going to take a quick glance at the Pokemon class and see what's happening here. I see that Pokemon have a instance variable name, an instance variable level, And they have two static variables, which are trainer and party size. And so they have default values here, which are ash and 0. Okay, I missed you. I hope you had a really great time working on this problem, and we are going to run through it together. And so first things first, we're going to take a quick glance at the Pokemon class just to get a bearing on what's going on here. I see that Pokemon have two instance variables, which are name and level. And so because they are instance variables, this means each Pokemon instance will have their own name and level. On the other hand, we have two static variables, which are shared by the entire Pokemon class. And these are the trainer and the party size. And these are initialized to some default values. And so that's very cool. We see that all Pokemon, every Pokemon in the entire Pokemon class, because the whole class shares it, will have the same values for Ash and the same values for party size. Next, we see that there's a constructor, and so that sets the name and level, and it increases the party size by 1. Now I think we're ready to start actually just jumping through main. We can look at these other methods later as they come up. And so now I think we're good to actually start stepping through main. So first things first, we say Pokemon P is a new Pokemon object. And so again, P or Pokemon will be a reference type, and it's not a primitive because the only primitives are, again, like our ints, all the number types, characters, booleans. And so P is an object. It is a reference type, which means when we declare this, P will store some random memory address, and then at that memory address will be the real Pokemon object. And so this is a Pokemon. Oh, what am I even writing? Pokemon. Okay. And so when we go into the constructor, we are going to set this dot name to be Pikachu. So Pikachu, this dot level will be 17. Then we increase the party size by 1. And so this means in the whole class, everyone's party size is now 1. And we also say Pikachu has the static variable because all instances in the Pokemon class share these static variables, and it is Ash. Cool. And so I've just put the static variables in blue so we know that they're special. They're shared by the whole class. So P is pointing to this Pokemon in memory. Then we have J. And so let's say this is a different little guy, and let's say it's at some other memory address. These numbers are just random, don't worry about them. I don't even know if these are reasonable memory addresses. I'm just picking them. And so we have J, and again, it is a Pokemon instance. And so we use the constructor, we say this dot name is Jolteon, this dot level is 99, super powerful. And then we again increase the party size by 1. And so party size is now 2, which means Jolteon will have a party size of 2. And it's also going to change it for Pikachu because it's a static variable, which means the whole class shares these. And Jolteon will also get Ash because, again, that's just one of the default values set here, and it is static. So everything looks good because these all match up. They're always going to be the same. Now, we print party size, and so party size currently is 2. So we will print party size equals or colon 2. Very cool. Now we are going to call p.printstats. And so the printstats method prints the name, the level, and the trainer. And we're calling it from the p instance, which means from p, when we look at name, level, and trainer, these variables are going to be Pikachu, 17, and Ash. Then we say level equals 18. Cool. So now we have some local variable in the main method, and it is level. It is a int, so it is a primitive type, which means 18 will be stored directly there. Then we call change, putting in the instance p and level. Very cool. And so we're going to open up a function frame. Let's do that in orange. And within the change function frame, we've been passed P and level. And so again, because we are passed by value, we will get copies. So Pokey is going to be a copy of whatever P was. And so that's this address, 1000. And level is going to be a copy of whatever was passed in here, which is 18. So now we have level is 18. So we got a copy of what this looked like. Then within the change method, we say pokey.level equals level. And so, as you recall, in pass by value, this memory address is referencing the exact same Pokemon as the one here. So when we say pokey.level, we're following this pointer, then we go to the level and we set it to be level. And so what are we going to set it to? We are going to set it to be 18, right? And this is because we're setting it to whatever level is. And so we will set this to be 18. Then we change level to be 50. And so again, within the change frame, level is this local variable, so we set it to be 50. And again, because we're doing pass by value, that doesn't affect the level that was passed in here. It doesn't affect this one because we got our own local copy. And so we change level to be 50. And one thing also is that we're in a static method change. And so we don't even have access to these instance variables, even if we wanted to. But regardless, local variables will overshadow like instance variables, static variables, because it's sort of like more relevant at the time, I guess, is the way we perceive it. And so level is going to be changed and it's this local variable. And then we set Pokey to be a new Pokemon, which is Voltorb, or with name Voltorb and level 1. And so when we change Pokey, again, we are just changing what this local variable has. And now it is no longer a pointer to this Pikachu in memory, but rather it is a pointer to a new Pokemon object somewhere else in memory. And so let's say this is some other address. And this is another Pokemon instance with the name Gengar, level 1, or sorry, where did I get Gengar from? Did I make that up? Voltorb, level 1. And then we set the party size to be incremented by 1. And this is a static variable. So when we change the party size from 2 to 3, that changes it for everyone. So now everyone has a party size of 3. And then, of course, trainer is Ash. Cool, so we walked through the whole constructor. And now the next line, we say Pokey.trainer is Team Rocket. And so again, Pokey is this local variable. It is a pointer to this Pokemon object in memory. So we follow that sort of pointer trail. And this Pokemon's trainer field is set to be Team Rocket. And so we change Team Rocket, but because trainer is a static variable, it's going to change it for everyone, you guessed it. And so now everyone's trainer is Team Rocket. And we can even just note that here. So it's really clear to us who's the trainer right now. And so that is all of the change method. We exit that now. And we're back to main after having called this. And now we do p.printstats. So what's going to be outputted here? We look at p and we see that printstats is going to ask for name, level, and trainer. And so the name is still Pikachu. The level has been changed to 18, and our trainer is Team Rocket. And I'm just doing this based off our little diagram that we've written. I'm trusting that our diagram is correct. Then we set Pokemon.trainer to be Ash. And so we're going to the Pokemon class and changing the static variable trainer. And this is valid because you're allowed to change static variables using the whole class name rather than an instance. In fact, that's even encouraged in better form than doing something like Pikachu.trainer is Ash, right? It's better form, but it's technically still allowed to do both ways. So we go to the Pokemon class and we set the trainer to be Ash again. Great. And so now everyone's trainer is back to Ash, and that affects it for all members of the class. The whole class sees this change, but it hardly even matters because in the very next line, we then set J.trainer to be Brock. And so again, this is that idea of you can change the static variable using a specific instance. So here it's J and we are changing the static variable trainer. It's just not the best form or like bad programming practice, but for this example, we'll go ahead and do it. And so we say J's trainer is equal to Brock. Oops, blue because it's static. And so once again, because it is static, it changes it for everyone. And finally, we call p.printstats again. And so now at this point in time, we see that Pikachu has named Pikachu still. The level is still 18, but the trainer is Brock. And so even though we changed Brock using the instance J, it doesn't just change the trainer. That's a tongue twister. It doesn't just change the trainer for J, it changes it for everyone because trainer is static. And that is the core idea. And so we've now walked through what main would output. It's these lines here. And hopefully that made some sense to you. And so I know static can be a pretty confusing topic, and sometimes you can even wonder, like, what is the point of this? But let's think about the variable party size right now. So what was party size really doing? It was essentially a counter for how many Pokemon instances were out there, right? And so we started with 0 Pokemon, and after making Pikachu, Jolteon, and Voltorb, we had 3 Pokemon out there. And so this is super helpful, and you can think of scenarios where you'd want this sort of static counter, right? And it's not really something that's pertinent to one individual Pokemon, right? But rather the class as a whole cares about this information of how many Pokemon are out there. And there will be plenty of times where having a static counter variable will be helpful. And so that is what main outputted. The second question is, on line 30, we set level equal to 50. Which level do we mean? An instance variable of the Pokemon class, a local variable in the change method, or the local variable in the main method? And so I believe we went over this, but just to be clear, on line 28, we set level to be 50. And so which level were we talking about? Again, we were talking about the local variable and change. And the reason for this being that within the change frame, like the local variable was right there. We didn't have to go searching anywhere else for it. And so when we set level to be 50, we look for a level, it's right there, that's what we change. And that is the way it goes. Now, if we were to call Pokemon.printstats at the end of our main method, what would happen? So let's take a moment to think about this. Pokemon is the name of the entire class, right? This is the whole Pokemon class. Now, is printstats an instance method or a static method? Printstats is an instance method. And if we called this instance method from the class, this would error. And that is just one of the rules of the compiler. You cannot call an instance method using the whole class. Logically, we can think about this. What does it mean to say Pokemon print the name, the level, and the trainer of the whole Pokemon class, right? Trainer might make sense because all the Pokemon share the same trainer. But if we wanted to print Pokemon.level, what does that actually mean? Which Pokemon's level? The Pokemon class or the whole like concept as a whole doesn't really have these ideas of instance variables or a name or a level. And so that's why it doesn't really make sense to try to call printstats or any other instance method for that matter using the Pokemon class. And so that is problem 1. Now we are going to move on to problem 2, to-do list. And so this is just a practice with int lists. Or I guess string lists here. And so a string list is very similar to an int list. It has two instance variables, first and rest. And so we can represent it something like this, like A, B, whatever, and so on and so forth. And so first is referring to this value. Rest is referring to this pointer to the next value. And just to sort of hammer in these ideas of like storing pointers, really somewhere in memory, there is this node, there is this node, whatever. And this node, when we say it's storing a pointer to the next node, really that means it's storing this reference to where in memory the next node is. And so you don't really need to think about that on a low level, but just to give you an idea of what it really means when we say it's pointing to the next node. So I want you to walk through this problem and draw out the box and pointer diagram that results from running the following code. And so that means draw all these int list nodes. And then we will come back together and work on this problem. Hello, welcome back. Hope you had a great time working with these linked lists, string lists. And so we are going to dig right in. First, we say string list L is a new string list with first eat and rest null. And so we'll make our new string list representation, which is going to have our first be eat and our rest be null. And we will say L is pointing to there, because L is a reference. String lists are reference types. And so L, the memory box associated, will just have a memory address of where this node is in memory, or in other words, a pointer to where it is in memory. Then we have the next line. And so we're going to evaluate the right side of the assignment first, as always. And so new string list of should and L. And so this means we're making another little string list instance where our first is should and our rest is pointing to what L is pointing to. And so because L is a pointer to this node right here, rest will also become a pointer to the same thing. Now we've evaluated this whole right side, which means we can go ahead and carry out the assignment. And so L will get reassigned to point to this new string list we've just made. Great. Then we repeat this whole thing again. And so we make a new string list with first here, and our rest is a pointer to L. And so, or rest is whatever L is. And so L is a pointer to this node. And so the rest of this new string list we're making right here is also a pointer to there. And now that we've made this whole new string list and we've evaluated the whole right side, we can carry out the assignment. And so L actually gets reassigned out to here. Then one more time, we repeat this. We make a new string list. And so I'm actually gonna move this out of the way a little bit. And we say it has first being sometimes, and our rest is what L is. And so again, L is currently a pointer to this node. And so our rest becomes a pointer to that node because we're getting the same thing. And then now that we've evaluated the whole right side, we can actually move on to do the assignment. And so L gets reassigned here. Cool, so we have this string list so far, and it's a chain where it goes, sometimes you should eat. Cool, I like that message, I'm always hungry. Then, in the next line in code, we make a new string list, or we declare our new string list M, and we say it's going to be what L.rest is. And so L is pointing to this object right here, this node, and the rest value is a pointer to this object, or this node with U. And so when we say M is equal to L.rest, we're going to become the same thing, which is a pointer to the U node. And so I'll just do this in green so it's a little easier to see. M is pointing there right now. Oop. Cool. Then we say R is a new string list of many and null. And so we will say R, many, and our rest is null. So R is pointing out there. And then in the next line, we do sort of the same thing as earlier, right? We make a new string list and its first value is potatoes and its rest is whatever R is pointing to. And so R is pointing, or is a pointer to many. And so potato, or this string list, points to the same thing. Now that we've evaluated the whole right side, we can go ahead and carry out the assignment. So R now actually points to potatoes, and I'm just going to move this so it's a little cleaner. And so R now points to the thing we just made because we've carried out this assignment. Then we say r.rest.rest equals R. So that's a little weird. So R is a pointer to this object, and so the rest is this object. This object's rest is this field. And so right now it's null, right? And so again, this is R. This is what R is pointing to. This is where r.rest gets us. And r.rest.rest is going to be changing this field. And we set it to be equal to R. What is R? Well, R is a pointer to this node. So this becomes a pointer to that node. So we've made a little circle here, right? That's kind of funny. Then we say m.rest.rest.rest is r.rest. So we follow out m, and m's is this node, and so m's.rest takes us to this node. This one's rest takes us to the next node, and this dot rest is this value here. So this is what we're about to change, and we set it to be equal to r.rest. And so again, this is what R is pointing to, and r.rest will get us here because it's a pointer to this next node. So we're setting this, the m.rest.rest to be equal to r.rest. And so we end up pointing here to many. And so we've executed this line. Then we say l.rest.rest equals l.rest.rest.rest. So we are going to look at this right side first. And so L is a reference here, and L's rest is a pointer here. So far we're one rest in. This one's rest is a reference to this whole node. And so now we're 2 pointers in. And this one's dot rest is a reference to this whole node. And so that is the right side. We've sort of followed this trail and we went in 3 rests deep, or in other words, we followed 1, 2, 3 rest pointers. And that ended up us at this node. So this is what the right side of this assignment is equal to. And the left side is just l.rest.rest. So L's rest. And so one way to do this is just to follow the pointers, sort of like rest, and that gets you here. Whereas doing rest.rest got you at this node. So we're saying L's.rest is this little like line that I've highlighted, this pointer is what we're changing. And so we're going to change it to point to the right side that we found earlier. And the right side of the equation was this node. Cool. And so that is where that's pointing now. And finally, we say L is equal to m.rest. And so M, we're going to look at this right side. M is a pointer out here. And rest, its rest is a pointer to this eat, right? Use rest, or this node's rest, is this linked list. And so we will set L to now point to this string list with eat. Cool. And so this looks a little messy, but there's a couple things we can do right now. So notice that nobody is pointing to this string list with sometimes, so we can just go ahead and erase it, because if no one's pointing to it, no one can reference it, no one can reach it. Similarly, no one is pointing to this string list with should. Even though should is pointing to other people, no one has tabs on should, so we can just erase it because no one could access it. And so the final result is that we have this string list. And so if we just started at M and we went through, it would go you eat many potatoes, right? If we start our R, it's going to be potatoes many, an infinite loop. And if we started at L, then we'll get an eat many potatoes, and this many potatoes loop goes on forever. And so we have our linked list. Very cool. Okay, the last thing we're going to do is go over helping hand. And so fill in the blanks of the methods find first and find first helper below, such that they return the index of the first node with item n, and that's an argument we're passing in to find first, or -1 if there is no such node containing that item. And so to give an example, if we passed in, let's say this int list or this SL list that looks like this, 3, 3, 7, let's say, and we said find first of n equals 3, or in other words, that's the item we're looking for, we want it to return 1 because that is the index of the first node containing the item 3. And so we're not going to return 2 because that's not the first one, and we're not going to return 1 because that's not the right item. We're going to return the index of the first node with item 3. And if we had asked for n equals 10, for example, on this linked list or this SL list, it would return -1 because the SL list does not contain the item 10. So that is an example of how it should work. And now I'm going to give you a second to pause the video and come back after you have tried implementing it. Okay, so now let's think about how we would actually start to implement this method. And so we can imagine, again, if we had some linked list structure, I shouldn't have erased this, I should have just kept it like this, right? What we're gonna wanna do is have some way of iterating through, right? Moving along our SL list. And as we do so, checking to see if we have found the item we're looking for and exiting upon the first time we find that item, right? Because we just want to return the first instance of it, right? And so I'm noticing that in our helper method, we have two variables that seem like they would be very relevant here, right? We have an index and a cur. And so I can imagine cur is going to be sort of this placeholder of how we keep tabs of which node we're currently at, right? And it's a node, which makes sense because we're pointing to these nodes as we're moving along. And then we have index, which is the actual number or how far along into the int list or SL list we are. And that's what we're going to want to return once we eventually find the correct element. And so knowing this and knowing that we're probably going to use cur as our placeholder of where are we in the SL list and index as our counter for how deep are we in, we can start looking at the helper method. And I'm starting with the helper method just because I think it seems to have the bulk of our work, right, as opposed to find first. And I think it will be more helpful if we first get the bulk of the problem down and then think about the specifics of how do we call our helper now. So I see that we have these base cases up, or we have these if statements, and then we have some other case. And so I think looking at the structure, it's safe to assume we might have recursive base cases here, and then our recursive case at the bottom. So what are our base cases? In what case would we want to return -1? Well, we would want to return -1 if we had looked through the whole list and never found the element we were looking for. And so, for example, if n was equal to 10, and we had this int list passed in, we might iterate through the whole thing, keep looking for it, and then we reach the end of the int list, and we've never found 10, which must mean it wasn't in there. And so we could say, if we're at the end of our int list, we must have gone through the whole thing, looked for that item, and never found it. Well, when would we be at the end of our int list? If cur was null. And because that is because the int list ends on this like null pointer, and so that's our first recursive base case. Now, in what case would we want to return index? Well, that would be if we were, again, traversing along, and let's say we were looking for 3, and so we have index 0, now we're at index 1, and the current node that we are at has the element we're looking for. Therefore, we want to return the index that we're currently at. And so we could say if cur dot item equals n, we'll return index. Perfect. And so cur dot item is our the current node we're on's value right here. And n, again, is that value we're looking for. Now, finally, the recursive case. Well, we're going to call ourselves because that's what recursion is. And so what do we pass in here? Well, the number we're looking for, n, never changes. So we can just pass in n again. What about the index? Well, as we're moving along through this array, the index is increasing by 1 every time. So we'll pass in index plus 1. And finally, what about the node? Well, let's say we're currently at this node and we want to keep moving along to the next one. How do we get from here to the next node? Simple. Our node has a handy little pointer to the next node. And so that is going to be cur dot next. Perfect. And so that is our helper method. Now the question is, how do we call this when we're first getting started? Well, we know that if we were passed this list again as our example, we would want to start at the very first node, and our index here is 0. Well, how do we access this very first node or sort of kickstart this process? Well, if you recall, the sentinel is our way of keeping track of the very beginning of our int list or SL list. And if you look in lecture, we'll talk about why sentinels are important. But the basis of it is that our sentinel is this reliable node where we always know it is sort of this reference for where our first node is. And so if you look here, we say this dot sentinel is a new node. So sentinel is this reliable pointer to where our start node is. And so sentinel.next will always point to the first node in the list if there is one. If the linked list or SL list is empty, sentinel.next will be null. But assuming it's not, then we can say sentinel.next will always be the first node. And this is something that's talked about in lecture, so you can learn more about it there. But, if we call find first helper, and again, that n, or the item we're looking for, is going to be the same, so we just pass that in. Our starting index is 0, and sentinel.next is the 0th node. This should get us started looking here. And so now in the helper, we can start at this node that was passed in by find first, and then traverse down and do our thing. And so that is the implementation of find first and find first helper. Great. And so now I have a conceptual question for you, which is, why do we use a helper method here? Why do we do this? Why don't we just have the signature of find first just be what find first helper is, right? Why don't we just make sure that the user always passes in index and cur and just not bother with this and get started straight on the find first helper? So take a moment to think about it, and then we will come back and do a fake discussion. Okay, hopefully you've thought about it. So why is it that we don't just have the user pass in the sentinel and the starting index is 0 every time, or sentinel.next and 0? And so one reason for this is that it is bad programming practice, right? Let's say I'm just some person who's using the SL list class, and I know, oh, I have this method find first, just based off the method name, I know it's going to give me the first element in the list, right? But if I'm just using the method, I have to know, oh, by the way, under the hood, what it's doing is iterating through, and it's using a node as a tracker, and it has an index counter that it's incrementing, and I have to know all this stuff so I can pass in those values, right? And those passing in 0 and sentinel.next have nothing to do with the task I want, which is finding the first instance of n. But I have to pass them in for some reason because that's how it was designed. The other thing is that what if I was calling find first and I was the user of this method and I just passed in find first, and I wanted to find the first instance of 10, but I passed in 1 million as my index. And then instead of passing in sentinel.next, maybe I did like sentinel.next, right? And so that is just absolutely incorrect. It's going to end up breaking our implementation because now we would return not only the wrong index, but we might miss, like we're not going to be looking at the very first node, right? Because we're skipping straight to sentinel.next. And so these are all reasons why you don't want to end up doing this and why it's better to have clean looking code and then call your helper methods under the hood, but the user does not have to know about them. And this method should honestly probably be private because again, the user does not have to know and should not know how you are implementing this method under the hood. All they need to know is that this method finds the first instance of my number that I passed in. And so that is why we use a helper method. Another reason you want to use a helper method in a different scenario might be if your code is getting super repetitive because you're doing the same like calculation or same whatever over and over again. And you have like the same sort of lines repeated in your code, it's better to just make a helper method and then call that helper method over and over. So that way your code is not excessively long and hard to understand. And it also makes it easier to debug because let's say you've written the same piece of code 100 times, and then in like 5 of them, you made a typo. Now you have to go fix all of them. Whereas if you had just made a helper method and then called it 100 times, if there's a bug, you only have to debug your helper method. So those are the reasons helper methods are super valuable and important. You should definitely be writing helper methods when you're doing your projects as appropriate, because it will make your life a lot easier. And that is it for discussion 3. Thank you for watching this video. Have a great rest of your week and make sure to drink water, get sleep, and relax. Bye.